Great. Welcome. So yeah, this first lecture is just going to be a bit of an introduction. I'll go through some administrative stuff about how the course is going to work, and then I'll do a really quick overview of like everything, almost everything that we're going to talk about. So we'll start with the intro. So just a little bit about me. I'm a precariously employed assistant professor at IGN. I am an igneous petrologist first and foremost, also a bit of a geochemist, but I mainly research really, really old stuff, which unfortunately we're not going to cover too much, which is a shame because it's really cool. So I've done a lot of work on komatiites, which are these kind of ultra hot lavas. They don't erupt anymore. The oldest one is the youngest one's 90 million years old, but the vast majority are older than 2.7 billion years old. And I guess I did my PhD in these fairly special ones from the Proterozoic, so kind of unusual. I've also done some work on norites, which are these orthoproxene and plagioclase cumulates that are also, you do see them at the present day, but they're a bit more rare. They're more restricted to an early period of Earth's history. I've worked on chromatites, which are these weird rocks, which is basically pure chromite, and peridotites, a mix of mantle peridotites from recent rocks and ultramafic cumulates from the Archean. I'm also a bit of a specialist in reading osmium isotopes and PGs, and I don't get to talk about them at all in this course, so that's a shame. So I've just been drafted in to cover this course for this block, but it is a new course. It's never been done before. This is merging two previous courses, one which was called Grundlegende magmatische petrologie, which was more on the kind of magma generation and crystallization side of things, and another called Lithosphärengeologie, which was more like tectonic settings, a bit more on, say, granites and evolved magmas and that sort of thing. So I cannot stress this enough, like, there's going to be problems. It's a new course. I won't have done this. I don't know which bits you guys are going to get well. I don't know which bits you're going to struggle with. So please ask me questions. If you don't understand something, there's a good chance I haven't explained it right, or the structure of the course isn't giving you all the basics that you need to get to understand what I'm talking about. So you have to just be straight up with me. I've got breaks in the lectures where I will stop and specifically ask for questions, but you can interrupt at any time. Yeah, so don't be scared. All right, the plan for the course. We've already done the Spain field trip. As I said, it's probably the hardest part of the course, and I think the reason for this is you saw a lot of volcanic rocks. A lot of them were very strange. So we had lamperites, which are quite weird and complex. We had this concept of metasomatism. We saw some subduction zone andesites, but they were this weird mix of like breccias and columnar jointed stuff, and so lots of weird stuff in Spain. So it's all downhill from here. It's going to get easier. So this week, I'll do this introduction. I'm going to talk a bit about where melting happens on the Earth, and then I'm going to zoom in on mid-ocean ridges and use those to talk about different types of mafic igneous rocks. After that, next week will be a blend of mid-ocean ridges and some mantle plumes, and we're going to use that to talk about magma crystallization. The following week after that, a bit more on mantle plumes, ocean island basalts, comparing alkaline and tholeiitic basalts, and we'll talk a bit about large igneous provinces. Then we'll talk about subduction zones and some more complicated processes that we can have when we're making and crystallizing magma. In the new year, granites and rhyolites, so these are kind of more evolved magmas, felsic magmas. We'll talk a bit about volcanology, and then finally we'll do a bit more about volcanology and try and bring it all back together in the context of the different tectonic settings that we've spoken about. If we have some time, I will talk about weirder magmas, but that's just a nice to have. Week 3 will basically just have a short recap lecture. I'll leave the time for you guys to ask questions. In the practicals, I'll be there, and you can come in and have a look at some of the rocks that we've discussed. We can go over exercises if you don't understand any of the calculations, that sort of thing. So that's just to get you ready for the exam. And then week 4 is exams. In terms of the skills you're going to learn, I think this is probably non-exhaustive, but these are the main ones. So identifying different types of igneous rocks, the key minerals, the sort of textures you might see. Hopefully we're going to understand crystallization and magma differentiation processes. I want you to understand mantle and crustal structure and the way this influences melting. Talk about mineral compositions. We'll do some basic phase diagrams, which I can't remember if you've encountered or not before, so we're going to start right from the bottom. Major element geochemistry, trace element geochemistry, and then we're going to kind of link all these different variations in magma composition and try and understand how that influences volcano types and the way they erupt. Yeah, and then we're going to put all of this in the context of different tectonic processes. Great. So we'll just do, this is like the whole course in one. We're going to do where and how does melting happen on Earth. So hopefully you already know that most of the Earth is solid, pretty overwhelmingly solid, and most importantly to this course, almost the entire mantle and the crust is more or less solid. The big exceptions here is the outer core is completely liquid, and obviously the atmosphere is a gas, the oceans are liquid, that's fine. So when we talk about making magmas and volcanoes, we need a way to melt the solid rocky parts to produce magma, and eventually that's going to erupt as lava. Just in really broad strokes, the composition of these kind of different major building blocks. The mantle is made of peridotite. We'll talk a little bit more about that in detail later. The oceanic crust is broadly basaltic, and the continental crust is andesitic or intermediate. You might sometimes hear continental crust being referred to as more like granitic, but essentially the upper crust is more felsic, a bit more like granite, and the lower crust is actually kind of like quite mafic. So it averages out at about intermediate. So rocks are complex mixtures of minerals. So when you melt them, they never just melt all at once, right? If we take an ice cube and we melt it, the temperature of that ice sits there at 0 degrees until the whole thing is melted. Rocks are completely different. We can start melting at one temperature and we'll get a little bit of melt, and then we could increase the temperature, for example, it will melt a bit more. And there's actually this kind of gap. It's completely solid at the solidus. That's when you first get the first tiny little bit of melt. It's completely molten at the liquidus. So most melting on Earth is partial melting. It's really, really rare to get 100% melt. And so when we melt a rock, both the melt and the residue that's left behind are different in composition to the original rock. So this is a major way of producing differentiation, like changing the composition of things on Earth. So as a really, really rough rule of thumb, mantle partial melting produces mafic or basaltic compositions, whereas if we melt the crust, we'll generally produce felsic or more granitic compositions. So you can see here, is that pointing stick still kicking around? Where did it go? Okay, sweet. Yeah, just really, really roughly, this is kind of our progressions. We start with mantle, melt it, make something more like oceanic crust. Here's a gabbro, and if we melt a gabbro, then we'll generally get something vaguely granitic, and we'll go into way more detail with that later. So where does melting happen? Geographically, this picture on the right is a picture of volcano distribution on Earth. In the resources for this week, I've actually put a poster up there where you can see in like insane detail where the 50,000 odd volcanoes are on Earth. So if we look at them compared to where plate margins are, they're overwhelmingly along the plate margins. So mainly along convergent margins. So you can see really obviously the Pacific Ring of Fire. So this is mainly subduction zones around here. There's also a load of volcanoes on mid-ocean ridges. They're not really shown on this map because they're underwater. There are also some rarer volcanoes that are away from the plate boundaries. Good examples, Hawaii over here, some of the other Pacific Ocean islands, and actually a bunch of stuff in the middle of Africa. And so this is what we call intraplate magnetism. It's within the plate. In terms of depth, melting is pretty much restricted to the uppermost mantle and the lower crust. The reason for this is in the upper crust, it's too cold, it's not going to melt. And if you go too deep in the mantle, then basically everything's at really high pressure. and it's very hard to melt stuff at high pressure. There are some exceptions. So in the early Earth, when the mantle was hotter, we might have got melting kind of in the deep mantle. This is a bit controversial. And even today, near the core mantle boundary, basically the core is so hot that it looks like there might be little layers of melt down in the lower mantle, but these are beyond the scope of this course, so you don't need to worry about it. So, thinking about the fact that our volcanoes are concentrated along plate boundaries, we can see that volcanism on Earth is mainly to do with plate tectonics. And there's basically three main ways of melting rocks, and these are mostly driven by plate tectonic processes. So the most kind of obvious one would be to increase the temperature. This isn't as common as you might think. So the second and third are going to be more what we're dealing with here. So you can decompress a rock. So if it is at high pressure and you reduce the pressure, it will melt. Or you can change the composition such that you make a new composition that has a lower melting temperature. This is mostly just by adding water or fluids. Yeah, I've said here, we're just doing quick overviews of the different tectonic settings. We're going to go into these in way more detail. So a good example of decompression melting. So this is mid-ocean ridges. So what's happening at a mid-ocean ridge is that the two plates are moving apart or diverging, and this produces something called passive upwelling. And what I mean by passive upwelling is there's no force like pushing the mantle upwards. Basically, the ridges are splitting apart. You can't have a gap, right? And so the mantle has to flow up to fill the space that would be left by the plates moving apart. So more specifically, this is usually called adiabatic decompression melting, and it's adiabatic because we're not adding heat to it. So this is it's the same idea as when you go high up in the mountains, it gets colder. You haven't pulled heat out of that air, you just drop the pressure. So this produces basalts and related intrusive rocks that make oceanic crust. There's a ton of examples. Mid-Atlantic Ridge is pretty famous. There's the Southwest Indian Ridge. Yeah, they're kind of all over the globe. The next setting we'll talk about subduction zones. So this is a kind of a changing composition, and hopefully you're a bit familiar with this, but what happens is as the plate that is subducting moves down, it starts to heat up. This heat basically breaks down hydrous minerals, release water. The water then reacts with the mantle above. Yep. Yes, sorry, those are just minerals that contain water in the structure. Yeah, yeah, sorry.
Is that from the ocean? The minerals?
Yeah.
From the ocean?
Yeah. So the oceanic crust, when it's forming at a mid-ocean ridge, basically you're producing all this hot volcanic rock. Yeah. It's surrounded by water. You start generating this really powerful hydrothermal circulation, alters a lot of the minerals and creates these hydrous minerals. So then when you subduct those, you basically have a bunch of water stored in minerals that you can release as it heats up. All right. So yeah, these fluids react with the mantle, and wet mantle melts at a lower temperature than dry mantle, so we call this fluid flux melting. It basically, as you're adding water, it's forcing it to melt. At subduction zones, a lot of the primary melts, the first things that we see kind of look like a basaltic andesite or maybe a basalt. It's a little hard to see because at subduction zones we have these really complicated crystallization and kind of magma plumbing systems that produce a whole range of magmas. The main one is andesite, but we'll talk about it more. We're actually producing more felsic, more granitic magmas as well. Also, you do get a little bit of adiabatic decompression melting in the back arc. There's sometimes a little bit of fluid in these, but the main process is that you're getting stretching again. So it's a little more similar to the mid-ocean ridge style. Best example is the Andes, for which andesite is named, because this is just a huge, I can't remember, 5,000, 6,000 kilometer long arc. Yeah.
What is assimilation in this context?
We will talk about that more later. This is if you have a hot magma passing through crust. Basically, it can melt it, and that melt can get incorporated. So assimilating, you might hear it called contamination as well. I tend to use assimilation because contamination has like a negative connotation. This is, yeah, anyway.
Question?
Yes?
I don't completely understand the decompression melting in the background.
Oh, yeah. So,
So the subducting plate comes down and then some decompresses, or?
yeah, the thing that I actually think this diagram has wrong, and a lot of diagrams have wrong, and you probably got taught wrong in first year, is that when the plate's going down, it's not being injected along the angle of the plate, right? So what's actually happening is these things are cold, they're sinking. So as it sinks, it sinks at an angle that's a little bit steeper than the plate. So if you imagine what that does over time, it actually starts rolling backwards because it's basically falling. And so you can't have a gap, right? So the arc actually moves out this way, and so you're stretching behind it. So most subduction zones have some sort of back arc melting.
Because it expands and it's
Yeah. So slab is rolling back, and the crust is stretching to accommodate that. Yeah, but we'll go into that in more detail in the subduction zone lectures. Okay. In terms of direct heating, this is probably the best examples are actually in terms of making evolved felsic rocks in the continental crust. Two ways we can do that. We can add a bunch of hot magma. So this is what happens at continental arcs. We're making a bunch of basalt or basaltic andesite from this flux melting. That's going into the base of the crust, and it ends up melting some of the stuff that's there beforehand. So we're adding heat by sticking a hot magma next to it. The other one that's probably most important at collisional zones, places like the Himalayas and Tibet, is basically if we thicken continental crust, and continental crust is full of these radioactive elements, then we're basically like building up a really thick electric blanket where all this radioactivity is heating everything up, and it can get hot enough to melt and produce granite. Finally, there are probably several types of interplate melting. The one we're going to focus on in this course, because it's the simplest and probably one of the more important ones, the mantle plumes. So with a mantle plume, it's kind of this combination of the plume itself is hotter than normal mantle. So plumes are these like hot, rising blobs of mantle. And so because it's hotter than normal mantle, it will melt more. But the actual melting is still this decompression. So this is still mainly decompression melting, but with hotter than normal mantle. The reason we get these plumes is the same reason if you think back to, say, like high school, if you did convection experiments where you put a Bunsen burner and you add a little bit of dye and you can see it moving around like that. We're basically heating the mantle from below because the core is really hot. And so basically you build up this hot layer next to the core, and every so often it breaks off and it rises up as a jet. Think like a lava lamp, except everything is solid in this lava lamp. Okay, so yeah, just to sum up, most magmatism and volcanoes on Earth occur along plate boundaries. Most melting is driven by plate tectonics. And the main ways we do this is by reducing pressure, adding fluids, changing the composition, or increasing the temperature. And we do see different styles of melting that are kind of associated with different tectonic settings. So does anyone have any questions after that? Okay, good. So that was the whole course. That's it. We'll talk really briefly about different types of igneous rocks and the concept of differentiation that I've already mentioned a couple of times. So loads of different ways of classifying igneous rocks. We can use the texture, we can use the mineralogy, we can use the composition. The kind of simplest broad-scale divide is that there are extrusive igneous rocks, so these are lavas, these are erupted, stuff like tuffs, ash layers, ignimbrites would fall into that as well. And intrusive igneous rocks that are not erupted. If we want to do like a really, really broad, like first-order distinction, the intrusive ones are going to be coarse-grained interlocking crystals, and that's generally because they've had a longer time to cool. If you cool more slowly, you have time to grow bigger crystals. And we shouldn't generally see a fine-grained ground mass because the whole thing crystallizes. For extrusive rocks, typically a fine-grained matrix. This can be glass, it can be these very, very fine-grained crystals, and they sometimes have coarse-grained phenocrysts. So these are like the larger crystals in the fine-grained ground mass. Yeah, so you can see on the top we have intrusive and extrusive equivalents. Granite's intrusive, rhyolite's extrusive. Diorite intrusive is intermediate, and andesite is extrusive, and then gabbro and basalt. We can also classify them more based on composition, which I kind of briefly did there. Generally, when we talk about mafic rocks, these are high magnesium, lots of iron. And this means that they are often dark because we have lots of ferromagnesian minerals. So ferromagnesian minerals is just anything that has iron and magnesium in. So olivine would be one, pyroxene would be one, amphiboles are generally ferromagnesian. So this tends to give you kind of like a dark colored rock. Felsic or silicic rocks are high in silicon, aluminium, sodium, potassium. And so because we have lots of quartz, lots of feldspars, these tend to be kind of light in color. I've put some alternative terms that you might see. I will probably interchange a bit between evolved, felsic, and silicic. I'm really unlikely to call them leucocratic, because I think this is a really dumb word. This just means light color, but you might read it in textbooks. Acidic, this is kind of old school, and it's to do with the fact that ions like magnesium act as bases. So these rocks are more acidic, these are more basic. But that's kind of an old school division. People don't tend to call them that so much anymore. On the mafic side of things, you might hear primitive. This means fresh from the mantle, basically. I won't use melanocratic, same reason, dumb word, and basic. These broad compositional changes are reflected in the mineralogy, which I touched on a bit. This is a really, really rough guideline picture. You shouldn't take this as gospel, but as a rule, in ultramafic rocks, we've got loads of olivine. In mafic rocks, we start to get more pyroxene plagioclase. Depends on the type of rock. Sometimes we'll see plagioclase first, sometimes we'll see pyroxene first. In intermediate rocks, you start to get more amphibole, biotite mica. And then in felsic rocks, this is kind of your classic granite assemblage of two feldspars, quartz, maybe some muscovite, biotite, amphibole. Yeah, so don't take these as gospel. It's really going to vary. So kind of one of the big concepts that we're going to talk about in this course is differentiation. And so this is the idea of gradually processes that change the composition of rocks. So you'll sometimes see this referred to as fractionation or evolving evolution. So as a magma differentiates, it generally goes from a more mafic composition to a more felsic composition. This is from a combination of processes. The biggest one is fractional crystallization, which is where it's cooling and crystallizing, and as it crystallizes, the crystals are falling out or being removed from the magma. There's also other processes such as assimilation, which we talked about briefly before. So yeah, this is really schematic thing of we start with basalt. It's got some basaltic composition. I'm going to call these green ones olivine. So it starts crystallizing olivine, and these drop out. As we remove them, we're removing this olivine composition from the magma. So the composition of the magma is changing, and we get some sort of crystal left behind. So maybe it starts crystallizing pyroxene next, plagioclase, and over this process, as we cool, we're left with progressively more evolved or more felsic magmas, and some sort of cumulate rocks, intrusive rocks that are left behind. So, differentiation on Earth is mainly driven by partial melting and then fractional crystallization and assimilation and other processes after you form the magma. There are other things, I mean, technically, say like weathering, making sediments is a form of differentiation, although we don't really talk about it in those terms so much. So with mantle melting, because it's partial melting, the melt has a different composition to the original mantle, and it has this similar effect. As we start with ultramafic mantle peridotite, and when we melt it, we end up with a high magnesium basalt or a picrite. These are still pretty ultramafic, but they are much less mafic than mantle peridotite. Yeah, I think that's all I have to say on that one. Okay, so igneous rocks can be broadly divided into intrusive and extrusive, mafic and felsic. Partial melting, cooling, and crystallization generally drive this change from ultramafic mantle compositions towards more felsic igneous rocks. And we'll call that differentiation. Does anyone have any questions about that bit? Yep. Yeah, it is. Well, I think we'll talk about that later today. Yeah. Yes. Anything else? It's quite a beautiful peridotite, that one, isn't it? I mean, look at those. That's that would have you guys hunting around in a stream bed for for garnet. Okay. How are we doing for time? Oh yeah, here we go. We reached the end. So yeah, just to summarize. Actually, you know what? I'm just gonna leave that up there. You can read it. I'm not gonna read those all off. Okay. Do we have any kind of final questions on that part of the lecture? Yes, Abdul.
The samples, are they in the hard rock?
Sorry?
The samples, are they in the hard rock?
Yeah, I'd say everything we're dealing with is hard rock.
Okay, so maybe it's same rocks from the first block last year, or?
I have no idea because I didn't teach first block last year, so yeah. Yeah, basically we're going to be dealing with a little bit of mantle peridotite, but mostly intrusive and extrusive igneous rocks. Yeah.